All right, everyone, section 6.5, specific heat. This is maybe one of my favorite sections that we'll cover over the entire semester. That's not to say I don't like the other ones, but this is just one of my favorites. Okay, so what we're going to be doing with this is we're going to be doing calculations to determine the amount of heat required to change the temperature of a substance by either 1 degree, 1,000 degrees, 0.1 degrees. Now, specific heat, in the absence of a phase change, so that means whenever it's liquid at 60 degrees and changing from a liquid at 60 degrees to a liquid at 65 degrees, we've not seen any phase change there. What we are going to do is we are going to look at or determine the amount of heat required to change that temperature of a substance using this equation. And this should look fairly similar or familiar. Q is going to be our heat. Heat is equal to mc delta T. Okay, now what are those different components? M is the mass of the substance. C is, I'm going to switch colors on my highlighter. C is the specific heat of the substance. And delta T is the change in temperature in either degrees Celsius or Kelvin. Okay, now those are interchangeable, Celsius or Kelvin, due to the fact that, well, the conversion, if a substance increases in degrees Celsius 1 degree, it increases Kelvin 1 degree, or sorry, 1 Kelvin. So that's a 1-to-1 conversion there. The specific heat of a substance is the number of calories required to raise exactly 1 gram of a substance by 1 degree Celsius or Kelvin. Typically the units are joules per gram degree Celsius, or joules per gram Kelvin. So here's what we've got: specific heats of specific substances. Now the one that you're going to want to be most familiar with is the specific heat of water in its liquid form. That is 4.184 joules per gram degree Celsius. Now notice, to change the temperature of solid water, well, it requires less heat. So from going from solid water to solid water at 10 degrees to 12 degrees or something like that, less heat has to be applied. But these are all some of those different values that we'll see. They are highly variable. One thing that I'd like you to recognize about this is that liquid water has a particularly high specific heat at 4.184. If you look at the rest of them, they're, well, with the exception of H2, most of them are less than 1. Now, interpreting a specific heat value. Substances with higher specific heats resist temperature changes more than substances with lower specific heats. So if you think about water, boiling water to go from, let's say, room temperature, which I'm just going to use degrees Celsius, so 25 degrees Celsius to 100 degrees Celsius, that takes a ton of energy compared to going from, or like, if you switch substances, if you're talking about, let's say methanol or something like that, or ethanol, to heat ethanol from 25 degrees Celsius to 100 degrees Celsius, it's going to require a little bit less energy. Now, examples, I just gave one, but due to the high specific heat of water, 4.184 joules per gram degree Celsius, water can absorb a significant amount of heat without experiencing an increase in temperature. So you can add a lot of energy or heat to water, but you might not actually see that temperature change. So water is a great insulator of, it's very resistant to temperature changes. Dry sand, on the other hand, the major component of sand, silicon dioxide, has a specific heat of 1 joule per gram degree Celsius. So on a beach, dry sand on a beach can be uncomfortably hot to walk on, due to the fact that it has a relatively low specific heat. Now here's an example of one of these problems. Remember the equation Q equals mc delta T. Okay. Now calculate the specific heat of water if 83.68 joules is required to raise the temperature of 4 grams by 5 degrees Celsius. Okay, so you might be looking at this and thinking, how do I do this? How do I include all of this? Well, the way that you do it is, or the way that I would recommend doing it is, I would look at my equation and say Q is equal to a mass, M, a specific heat, C, delta T. Okay, now our Q value is going to be heat, which we see as joules. Our delta T, well, we're changing this water by 5 degrees Celsius. So 5. Now this question is asking us to calculate the specific heat of water. We know what the specific heat is based on what we've seen previously, but this question isn't asking us to do that. Instead it's saying, based on these values, what is the specific heat? So all that we're going to do is rearrange this equation to be Q over M delta T equals C, because C is our specific heat. So I'm going to plug all this information in. I'm going to say 83.68 joules divided by my mass, which is 4.000 times 5.000. So 83.68 divided by 4 times 5, which is 20. Well, lo and behold, my answer is exactly 4.184, which is exactly what I had seen in my, or what we had seen as a literature provided value. So joules per gram degrees Celsius. Now, just a little bit of an aside. I really like this problem because it gives us all the units. It gives us our heat in joules. It gives us the energy. It gives us the mass. And it gives us the temperature change. So it asks us to basically use this Q equals MC delta T, plug these numbers in, and solve for C. So I think that in the event that you're ever, or if you want to know where to start with specific heat questions, get very comfortable that Q equals MC delta T. If you can do that, then you can do the algebra to manipulate that equation to get it to, well, basically do what you want. All right. Now, our next question. What is the final temperature after 1485 joules of energy is added to 16.7 degrees Celsius of water, okay, water, at 23.4 degrees Celsius? How do we start this? We've got a Q equals 1485 joules. We've got a mass, which is 16.7. We know our substance, which is water, and I'm going to say C is 4.184 joules per gram degrees Celsius. Sorry, I forgot my mass as units of grams. The last thing, though, is delta T equals question mark. Okay, so you might be looking at this and saying, I don't really understand how to do this. Well, what we're trying to figure out is this delta T. So we need to know what our change in temperature is. Now, what we know is our T sub I. I'm just going to use I for initial. If you're taking a physics class, maybe let's see T sub 0 or V sub 0 for initial velocity. But I'm going to use T sub I, indicating my initial temperature is 23.4. Okay, now 1485 joules of energy is added. That's a key word right there. So we're adding heat energy, we're adding Q to our water sample. So what that means is our temperature. Is it going to go up or is it going to go down? I'll drink my coffee while you think about it. Yeah, let's go coffee. Okay, well, our final temperature, it's going to be higher because the energy is added to our water. So I'm going to say T sub F equals X. Now, for change in temperature, what I'm going to do is I'm going to say delta T is equal to T sub F minus 23.4. My final temperature Subtracted from that is my initial temperature, which will give me my change in temperature. Now that's what I need to figure out. So I'm going to set up my equation. 1485 is equal to 16.7 times 4.184, and then T sub F minus 23.4. I'm going to divide each side by 16.7 times 4.184. Divide. So 16.7. So when you use that number, that you got that structure right now, what we're going to do is divide by 16.7, multiply that by 4.184. And once we do that, 1485 divided by 16.7 times 4.184, close parentheses, 21.25 is equal to T sub F, our final temperature, minus 23.4. Add 23.4 to each side, and we're left with 44.65. Based on sig figs, we got to round that to 44.7. So our final temperature, T sub F, is 44.7 degrees Celsius. That would be our answer, which makes sense because our temperature went up based on all this energy being added. So heat changes during solution formation. Heat changes occur during a solution formation, which can be endothermic or exothermic depending on the solute. The enthalpy of solution is the amount of heat absorbed or given off during the process. The temperature depends on three things: the identity of the solute, the amount of the solute, and the amount of water. So what this is, so if you added something like sodium hydroxide, NaOH, solid sodium hydroxide into DH2O, what you're going to see is a sodium ion and this hydroxide ion form. And simply that dissociation, that's going to evolve some heat. So the water solution that you've added this to is going to increase in temperature. And so that's just something that you have to consider, that sometimes the production of a solution will cause a temperature increase to take place. Sometimes it will cause the temperature to decrease. It all depends. All right, well, I hope this helps, and we'll proceed on with Chapter 6 in the next video. Thank you very much. Have a good one.